So tonight we have a bit of a special treat. Instead of just looking at a board, we have something a little bit more engaging. We welcome Navinda Kottege and his team. So there's a few of them around. This is a pretty exciting talk. There's been obviously some news about some of the work of these guys recently. So I'm not going to yabber on too long because I'm sure that there's going to be many, many questions. So we'll make some time for them. Feel free to ask questions along the way. If you can, just put your hand up and that way I can come and give you the mic so that anyone at home can hear your question as well as the answer. Without further ado, take it away. Thanks, Navinda.
Thanks, Michael. Can everyone hear me clearly? Perfect, thanks. All right, so welcome everyone. I'm Navinda Kottege. So I'm the group leader for CSIRO's Robotics and Autonomous Systems group. I'm also the principal investigator or the team leader for the CSIRO Data61 team that competed in the recently concluded DARPA Subterranean Challenge. So today's talk will be about that. And as Michael said, do stop me and ask questions. If it's going to turn into a discussion, we'll move it to the back. So I do have a lot of material that I use that I've used in multiple presentations. So bear with me if it seems a little bit incongruous at places. I'll try my best to tell a coherent story. All right. So in today's talk, I'll briefly try to cover some of these. What the DARPA Subterranean Challenge is and what we did and why it matters. So what we did is kind of spoiled by some of the images, so I do apologize for that. So in terms of the Subterranean Challenge, so what is it? So first of all, DARPA. How many of you here know what DARPA is? Quite a few, good. So for those who don't know, DARPA is the Defense Advanced Research Project Agency. That's the premier defense research agency funded by the US government. They've been around for a while. And before they picked up the D in the acronym and they were called ARPA, they invented the internet in the 60s. So that's how big they are. And more recently in the past 20 years or so, they've started organizing a number of robotics challenges. And in the early 2000s, they had the aptly named DARPA Grand Challenge. So that was to get uncrewed vehicles to drive across the Mojave Desert. And that literally kickstarted the autonomous vehicles in autonomous vehicle industry because it wasn't a thing back then. So Google hired the winning Stanford team, and that's what turned into Waymo. And more recently, they had what was called the DARPA Robotics Challenge, which was held between 2012 and 2015. And that particular challenge was inspired by the aftermath of the Fukushima nuclear disaster. And that was to address the technology gaps in sending robots and autonomous systems into areas like the disabled nuclear power plant. So fast forward few years, and back in 2017, they announced the next iteration of the DARPA challenges. It was called the DARPA Subterranean Challenge, as the name suggests. It was to access subterranean environments, and they divided the environment into 3 subdomains. First one was man-made tunnels, such as mining tunnels. The second one was underground urban. So that is any built infrastructure or built environment underground, such as sewer systems, subway systems, any industrial infrastructure you find underground. And then the third one was natural caves. That kind of is self-explanatory. So the whole point of that challenge was to send teams of robots into these unknown environments and essentially do a scavenger hunt for various artifacts that they place in the environment. And these artifacts, you'll see a little bit more in the next slide. So these artifacts were representative of things that you'd find or would want to find in the aftermath of either a natural disaster, industrial accident, things like that. So thermal mannequins representing human survivors, high concentrations of carbon dioxide, backpacks, fire extinguishers, mobile phones, climbing rope, hard hats, vents, air vents, drills, and then they had a special DARPA cube, which was, I don't know how to describe it. What's that? So it emitted Bluetooth, or was it Wi-Fi? Bluetooth, and it changed color. So that was to trick any visual only artifact detection. So in the next one, hopefully the video will play. That'll give you a quick overview of what the challenge is. This place, let's see. Do we get audio? Maybe not. It's meant to have audio.
Leaders. A valid report earns 1 point, but teams are granted only a limited number of reports, so they can't just guess until they get lucky. Sound easy enough? Think again.
To make it clearer, should I can just try to explain it. Okay. Yeah. So this video is about how you score points in the challenge. So most of it is quite visual, but I'll try to fill in. So it'll show you a bit about the artifacts that you'll find and the type of challenges that you'll find. So in case it wasn't clear in the beginning, you don't have GPS in the underground environment, so the robots wouldn't know where they are. So you need to go into this environment, map the environment, localize yourself in the environment, but also localize these artifacts. So there are 2 tasks. So one is to correctly classify the type of artifact, and then the second one is correctly determining the location, the XYZ location, relative to a reference frame provided by DARPA. And if you get the correct class of the object and the location within a 5-meter error bubble, you score a point. So, and you get 1 hour to do this. And these are some of the challenges that they have. So there could be dynamic obstacles. There'd be things like smoke. They'll fill the circuit with smoke. There are sharp drop-offs, vertical shafts, slippery terrain, narrow gaps, low overhangs, all sorts of terrain challenges. And on top of that, the environment itself makes it very difficult for radio communication. So DARPA doesn't artificially throttle the communication, but it's just the nature of the environment that does that. So just to give you an example, one of the circuit events that we had to do in the lead up to the finals, it was in a uncommissioned nuclear power plant in Satsop, Washington. And that had 2-meter thick lead impregnated concrete walls. And as you can imagine, that's not very friendly for any form of radio communication. Oh, and the other aspects of the challenge, which would have otherwise been covered in this video, is you get 30 minutes to set up, and then you get a 1 hour run. During the 30-minute setup, you have a limited number of people allowed to set up the robots. We get a pit crew of about 10 people, but once the clock starts for the run, only 1 person, the designated human supervisor is the only person who's allowed to connect to a computer that can talk to the robots. So during the 1 hour run, you have only 1 person, 1 human connected to the robots. Oops. So that's another video that usually has sound. We'll see. Oops. So this is a video showing the final scores, and it will show you some of the artifacts that you that I described earlier. So you'll know what it looks like inside the course. So that's a drill. You'll see a backpack soon. That's climbing rope. Helmet. Mobile phone. Another helmet. I'm waiting for a human survivor. Hopefully we'll see one soon. No, another rope. Oh, that's a DARPA cube. That's the one that I was mentioning earlier. Oh, well, I'll skip to the next. So a little bit about the history of how this came about. So I mentioned back in 2017, DARPA had this call for proposals to compete in this challenge. So our team from CSIRO, we put in a bid along with 2 other partners. So we had one subcontractor, our spin-out partner, Emerson. For those of not familiar, Emerson is a drone autonomy company based here in Brisbane. They spun out from our lab in 2018, and they've grown from about two people. There were 5 people who started, and now it's grown to about 120 people in 3 years. So it's a great success story. And we also partnered up with Georgia Tech in Atlanta, Georgia. And when we submitted our proposal, DARPA selected just 7 teams from all around the world to be funded to compete in this challenge. So we were one of the funded teams. There were 5 other self-funded teams as well. And out of the funded teams, what's significant is we were the only non-US based prime organization. So that itself was quite good to kind of be recognized for what we can do. And then the challenge started in September 2018, and the way they staged it was based on those subdomains that I mentioned earlier. So the first circuit event was the tunnel circuit, and that was held in August 2019 in a coal mine in Pittsburgh in the US. So we took robots over, we competed in that challenge, and we were 5th in the leaderboard. And then the next circuit event was the urban circuit event, which was that's the nuclear power plant that I mentioned earlier. So that was in February 2020, just at the cusp of COVID become a worldwide pandemic. So we traveled to the US, went to Washington State, and we deployed our robots in this nuclear power plant, which was pretty exciting. And we were 4th in the leaderboard. So we were slowly but surely creeping up the leaderboard there. And we were in pretty good company because the other teams that were competing were pretty big names in the area of field robotics. We had teams from NASA JPL competing along with MIT, team from Carnegie Mellon partnering up with Oregon State University. We had teams from University of Colorado, Boulder, and yeah, so quite a formidable lineup of teams. And there was a team from Oxford, combined team from University of Nevada, Reno, Oxford, and ETH Zurich. So now this slide shows some of the robots that we deployed and our team based in Brisbane. Okay, sorry. Okay. So there's another video which may or may not work. So the next video is to show the final score. So what DARPA did was pretty fantastic for the finals. Before that, rewind. So because of COVID, they meant to have another cave circuit event in August 2020, which had to be canceled due to COVID. And what they did was they encouraged all the teams to try and hold a cave event locally. And we rose to the challenge, and we did our own cave circuit event in Chillago, far north Queensland, where we took our robots and we did a DARPA-like event. Deploy the robots in the cave. We set up the artifacts, and we didn't tell our human supervisors what the course was like. So they didn't know, they didn't have prior knowledge. So we got Fletcher here, who was one of the human supervisors. Then we got all the data, we logged all the data, and we sent it to DARPA, and they were very happy about what we've done. And similarly, they got information and progress reports from the other teams as well. And then they selected 8 teams to compete in the finals. So we were selected to be in the finals that was held in September this year. Even we weren't quite sure how DARPA was going to pull it off, because they said the finals course was going to be a combination of all 3 subdomains. So we were also really trying to figure out how in the world is DARPA going to have a location that's going to have man-made tunnels, natural caves, and underground built environments in the same location. So they surprised all of us. And what they did was they went to a location called the Louisville Mega Cavern. That's in Kentucky. And it's a massive limestone quarry that's dug on the onto the side of a hill, and they built this massive course, all artificially made, that had all 3 elements in there. You'd have seen in the previous video, if you remember, I'll play another video. So you have the entrance, you go about 20 meters in, and then you get 3 entrances to the 3 subdomains, tunnel, urban, and cave. And then inside, they would intertwine and form a maze. So you have interconnection of the courses inside. And just to give you an idea how much all of this costs. So even we didn't know initially, it was only recently that we got to know. So DARPA spent $82 million running this competition. So that would give you an idea of the level of investment that they put in to make this work.
Just a question on that. So they've spent this $82 million. What are they hoping to get out of it? And some of the teams gone further with it? And I'm actually going to give you this microphone because I think it's much better.
All right, thanks, Michael. Again, as I mentioned earlier, DARPA has this history of really kickstarting new areas of technology. So they take pride in being able to catalyze new domains of research, new areas of technology. And the very nature of a DARPA project or a DARPA challenge means that you can't just pick off-the-shelf technology that's already available, cobble a solution together. That's not how DARPA sets up challenges. So they set up challenges in such a way that you really have to innovate and really push the limits of what's possible. And from their point of view, that's the investment. So they invest this sort of money, and that's what they expect to see the state of the art in this sort of technology be progressed. And what they did was, for each of the funded teams, they provided funding for participating as well, for competing. So for example, we received $1.5 million per year over 3 years from DARPA to compete. And we supplemented that with significant co-funding from CSIRO for us to be able to develop this technology. So the next one shows this course in the Louisville Mega Cavern.
We're in the Louisville Mega Caverns because it gives us wide open canvas to be able to paint our vision of what the Sub-T Challenge final event is. A mashup of 3 different subdomains: tunnel, urban, and cave. Each of the circuit events was focused on a particular subdomain, and that allowed teams to really zero in on what technologies work for that subdomain. The final event is about putting all of that together, bringing it into an integrated capability in that epic grand finale course. Join us for the final event, 21st through 24th of September. You can watch us on Sub TV.
So that was Tim Chung. He was the DARPA program manager who ran the whole project. So you might have gotten a glimpse of the 3 subdomains that were all artificially made inside the Louisville Mega Cavern. Now, we faced some challenges due to COVID. So we were pretty enthusiastic. We were really hoping to get out there, get the robots in the course, and make this happen earlier this year. But due to COVID, we weren't able to travel. So the Brisbane-based CSIRO team didn't get to travel because of COVID risks. So what we did was we shipped our robots overseas. We shipped, put them in crates, send them over to the US, and we had our challenge partners. Emerson, they were able to travel, and so was the guys from Georgia Tech, and we also have a CSIRO office in the US, and they also managed to send some personnel over. And we also were lucky enough to have some of our lab alumni who were already working in the US, and they volunteered their time to come and help us. So what you see on the top left-hand photo is the actual fleet of robots that we sent to the US. So 2 Boston Dynamics Spot robots, like the one over here, and 2 tracked robots. They're actually built by a Brisbane-based company. The tracked robots they're built by a company called BIA5. And then we have the 2 drones from Emerson. And on a side note, we still haven't received those robots. They're still stuck in customs in Brisbane. So it took about 10 days for the robots to be shipped from Brisbane to Louisville, which was fantastic. But on the way back, it's been 8 weeks and counting, and we still haven't received the robots. So shipping robots internationally is extremely hard. And this is a spare one that we kept in Brisbane. So that's why you have this one here. And so what we did was we hired telepresence robots in the US, and we were constantly connected with the team from here. So you'd see some images of myself and some of our team members connected via the double robots, talking to the team that was in the US. We were not only were we encouraging them, we actually did a lot of technical support as well. So down here you'll see an image where they actually had to do some upgrades to or modifications to the electronics of the robot while they were there. And then the team that actually went there, they've never done any of this stuff, because we couldn't send our mechanical engineers, we couldn't send our electrical engineers, we couldn't send our software engineers, and everything had to be remotely supported. And not only that, that they were in the US East Coast time zone, so most of us switched to working during US East Coast time from here in Brisbane. So down here, you'd see Fletcher and a few others. So this is around 2:30 in the morning from the lab. So they were constantly connected, providing support for about 2 weeks. That you see in the bottom left is the view that that we get from the telepresence robot. So that's me logged into one of the robots, and that's what I saw over there. So given all these challenges, even though we were pretty excited about our technology and quite confident of doing well in the beginning of the year, given all these challenges, we had to really lower our expectations. Like we had our bar really low to a point where our goal was don't embarrass ourselves. So that was how low our bar was at that time. Yeah, so I'll play this video. I think, yeah, this is from an onboard camera of one of our spot robots. So this will show you what I mentioned earlier about how the course opens up into 3 subdomains. You'll see that in a little bit. So there you go. So rightmost is the cave circuit. The middle one is the tunnel circuit. And on the left-hand side, that's the urban circuit. All right. So yeah, so we send the robots over. So and the way the final event was structured was they first had a preliminary round. So they had 2 runs, 2 30-minute preliminary runs. They were scored runs, but the score did not carry over to the final. So that was mostly to let teams get familiar with the course or parts of the course. And we completely surprised ourselves by
Just
winning
wondering
the preliminary round.
which robot's taking the footage here? Is that a spot robot?
Yeah,
or one of the
that's a
others?
spot.
Okay.
And just on that note, you've got 3 different robots. Do you use them all, or?
Oh yes, good point. So the reason why we selected different types of robots, I have another slide further on, is to deal with the different types of mobility challenges that these courses throw at you. So the track robots are great. They can go pretty much anything. However, they have a size penalty because they're wide, so they're not that great at going through really narrow gaps, and they're not that great at going up and down stairs. So for narrow gaps and stairs, that's why we got the spot robot. So the legged robot that's more capable of going up and down stairs, going through narrow gaps. And then these courses also have vertical shafts, big caverns with high alcoves and all of that. And that's why we had the drones. And then the drones were actually carried on top of the track robot so that it can be deployed when there's a opportune time, because the drones have limited endurance. So they can fly for about 15 minutes, whereas the track robots can last for hours and hours. And so that was our kind of deployment strategy. And we did deploy all the robots. And I'll tell you a little bit more about that later. So as I was saying, we had the preliminary round and we completely surprised ourselves by winning the preliminary round. So we came top of the leaderboard of the preliminary round. Suddenly we became the team to beat for the other teams, which was quite an interesting situation to be at after all the challenges that we had. And then came the prize round. Now, given that we topped the leaderboard in the preliminary round, that meant we go last in the prize round. So that's what they did. Like they looked at the leaderboard of the preliminary round and they kind of flipped the order. So the lowest scoring team goes first and the highest scoring team goes last. And and also what they did was they sequestered the team. So each team wouldn't know the other team's scores. So for example, given that our team went last, they were kind of locked away in a room and they didn't get to talk to us back here in Brisbane. Yes, question?
Testing. Okay. What was so this was like the finals of the challenge. What was the criteria that the teams like robots or work was based on?
You mean to get to the finals?
Related to the finals.
Yeah, so as I mentioned earlier, it was staged over 3 years in multiple circuit events. So we had 3 circuit events. So DARPA evaluated the performance at each circuit event. So So they had a pretty strict reporting requirement as well. So for the whole 3 years, every month we had to submit technical reports about our performance, how we are progressing. And then before each circuit event, few months before, you need to qualify. So there's a qualification requirement. So they'll give you certain qualification criteria. You need to perform those maneuvers, you need to perform those actions, create videos, provide a technical report, provide it to DARPA. So that's how you qualify to participate in each circuit event. And when you go to the circuit event, then they actually look at your overall performance, how well your robots perform. And then at each phase, then they'll let you know whether you're funded for the next phase. So we were successful in maintaining our funding throughout. And then they looked at the performance of the 3 circuit events overall, and then they selected 8 teams out of the original lineup of 12 teams to go into the finals.
Specifically to the aerial drones, is there a reason why you had such large drones rather than smaller ones? Because being subterranean, I would think smaller drones would be generally better.
Yeah. So hopefully that question will be answered in another slide. I'll answer that in a bit. So now in the finals, so as I mentioned, we went in. We then got to know the scores of the other teams, and I won't give that bit away. It's more exciting later on. But then DARPA had a really nice production, so they presented it in a way similar to how they do the Super Bowl or like sporting events in the US. So they had commentators, they had an expert panel, and they streamed it on YouTube, but not live. So it was delayed by 24 hours. So I'll show you some footage of that broadcast. Again, it might be a bit tricky because the audio is not good, but at least you'll see the footage. So the next video that you'll see is at the beginning of our run. Oh, and the way they show it, it's not clear, but all teams are not in the course at the same time. So it's one team at a time in the course. So you'll see the clock on the top of the screen in the next one. So that's a 1 hour run. So we got, this is about 5 minutes into our run. So you'll see.
And I think their point was they wanted to make sure that these are the slow and steady places that where they could get to. And there was a lot of really interesting mobility in tight spaces, even with these. So their vehicles really performed tremendously, I think, and they were happy with that as we talked to their team members as well.
Yeah, and here's another look of one of their tracked systems as you see the lights on board. And this is actually one of their marsupials, meaning there's a UAV on top of the UGV, could potentially launch off and explore a little bit higher.
And there was definitely some strategy that they were using as we watched through this
So
run
our
on
score is
when
still
and
0.
where they
It's,
used those UAVs.
And again, this
53
is
minutes to
from
go.
their prize round. Just within those first 7 minutes, we're running all of these teams' highlights as if they're running on the course at the exact same time. So no, if you're wondering if we've got 150 robots out on the course, that is not true. We've only got.
All right. So now what happened was our human supervisor, Brendan Tidd, he decided to deploy one of the legged robots. So just to make it more Brisbane, we named our legged robots after the Bluey cartoon. So the 2 robots were Bluey and Bingo, and this is Chili. She didn't travel. So Brendan sent Bingo down into the cave circuit, the rightmost circuit. And what happened was it went out of comms within about 5 minutes, and we never saw that robot again. So through the whole run, we never got that back in radio within radio range. And then since it went beyond comms, then Brendan decided to deploy another one of the robots. So I think what you saw there, that's Rat. So that was a tracked robot. But unbeknownst to us, what had happened was Bingo had traveled right to the end of the cave circuit within about 20 minutes, done a fantastic job in going really deep into the circuit, collecting a lot of artifact reports, doing a lot of mapping. But then
well, and I think
this is what it was doing in the last minute or so. It reached a really rough area. And yeah, that was a water puddle, and you'll see water dripping as well. So, so it got disabled with all the valuable data still on it, but it was disabled, so it couldn't come back. And the next one, I'll show you what the operator saw from the base station. So this is what our operator sees. So if you can read some of the things, so you'll see the time remaining, you'll see the score. So you'll see bingo going off, the green robot. So that's bingo going down the cave circuit. And then there's rat, the purple one that also gets disabled within 20 minutes because it gets stuck on a rail and its track comes off. So bingo goes beyond radio range there. So we don't know where it is. Comms lost. And then Bluey is deployed. So the yellow one, that's Bluey. So she's exploring another area of the circuit. And you'll see after a while, it actually it finds bingo, comes within radio range of bingo, gets all the data that bingo had, and valiantly tries to come back home, come back to comms, because at that time, comms lost for Bluey as well. And then at the 40-minute mark, you'll see what happens. So because Bluey briefly connected to bingo, all these new areas of the map becomes visible to the operator. That's how Brendan knew that there's another area of the course over there. So we are collecting some points. So you'll see 17 points, 900 seconds to go. So we still have Bear, so that's the other tracked robot. And what you see on top, those are the artifact reports that come back to the base station. And the human supervisor has to verify the artifact reports and send it back to the DARPA server, and then you get a score. Question?
So are they not in a mesh network where you can like leverage the signal off them when they get closer to each other, or you have to come back to base, which at the other end of at the entrance of the tunnel?
No, they are on a mesh network. So each of the agents are a communication node. On top of that, we are actually carrying communication nodes on our track robots, and we are dropping them along the way as well. So if you see some of the, maybe I'll play it again. You'll see some blue or cyan squares that are dropping along. So those are the communication nodes as well. Yeah. You're giving the punchline away. So again, so you'll see the 4 UGVs plus the two UAVs which are on 2 of the UGVs. So bingo goes beyond comms, and then this time, if you pay attention, you'll see the different colors for the different artifacts that we're detecting along the way. So we detected a drill and a backpack. So just 2 points at this time. Yep, we found another drill, fire extinguisher, backpack, another fire extinguisher. So Bluey gets some of the mapping data from bingo back. Found a helmet and a rope that bingo had found that came back through Bluey back to the base station.
I have another question. Sorry.
Yep.
I guess like as like he mentioned down the front about the communications, like being out of range, just interested like from an electronics kind of data perspective, because this is real-time mapping. How long is like the data stored for? And like did in this challenge, like did anyone measure like did anyone look at like how long, like how much data each of those robots could collect and how they were stored and what happened with that information afterwards?
Yeah, so we did a fair bit of work on that. And so the physical connectivity is provided by what's called reagent radio. So we have one of those in here as well. So we buy these radio modems from a US-based company called Reagent. So they're fantastic. They're built for underground operation. They have dual band, 5 gigahertz and 2.8, 2.4 gigahertz. However, on top of that, we built a communication layer which we call mule for data muling, and that I guess that's a network state aware protocol that connects to other robots and then is aware of the available bandwidth, because just because a robot is within radio range, that doesn't mean that you got good signal quality. So it'll be aware of the communication bandwidth, and then it'll decide how much data it sends through. And we already do a fair bit of data compression. So we are not sending the raw point cloud. So we are sending what's called the surfels from our SLAM system. So it's a fairly, so even though you see, this is what you see here is not a point cloud. So this is a meshed surfel map that you see at the base station. So we have to send our surfels, we need to send the artifact reports, and also the navigation information has to be exchanged, because we are doing multi-agent navigation as well. So we are doing what's called multi-robot task allocation. So when the multiple robots are deployed, they actually talk to each other to figure out which path they need to go into. So because we are going beyond communication range, we had to rely a lot on autonomy. So none of this is radio control like this. None of this is the operator using a joystick to operate the robot. So at the base station, what we have is we have high-level missions that we allocate to each of the robots when they're sent in. So our exploration algorithm, it's a frontier-based exploration algorithm. And each of the frontiers become a task. And then since each of the robots are talking to each other, then each of the robots have to figure out which frontier or which task they chase. And then they use auction-based bidding system to figure out which robot goes after which frontier. And that's how all of that works. And the communication network has to deal with that traffic, the artifacts, the surfels as well. So yeah, all of that was taken into account. And in fact, what you see here, which made us really happy, was this is exactly how the system was supposed to work. And in the finals, it worked exactly how it was designed, because we had robots getting disabled, we had agents failing, but we didn't have a catastrophic failure for the overall system. So our overall system was still resilient, and it did exactly what it was designed to. And now I'll show you another view of the DARPA footage. So this is less than, what's that? Yeah, 7.5 minutes to go.
Might as well get them out on that course, see what they can do as CSIRO Data61 pops on up along with that attempt and their score.
Taking off.
Ooh,
Yes,
there it is.
So this is me as a layman saying, get the drone up. But what was interesting is the drone is not for discovery. The drone was to get it out of
the audio because it's not clear. So what's happening here is, as I mentioned earlier, you'll see that in the next video as well. So we had Bingo fallen, Bluey goes and meets Bingo, gets the data, tries to come back, and then Bluey falls as well. So now 40 minutes in, so we got 20 minutes to go. And then our other tracked robot is also disabled. And we only have one operational tracked robot right now in the last 10 minutes. And that's got a drone on top. And the other tracked robot that had the drone on top, because it got disabled in a narrow cave, we couldn't deploy the drone, because if we deployed the drone would have crashed. And we didn't want to take that risk, because if the drone crashes, given that we are doing multi-agent SLAM as well, there's a risk of that corrupting a whole SLAM map. Then at that time, our human supervisor, Brendan, roughly knew where the fallen robots were, because he got enough map information coming through. But not enough of a bandwidth to get all the data that he wanted. So he wanted to send the remaining agent within radio range to get the data back. Now, given that he had the drone on the back, we have a much bigger bounding box for the robot, and the cave circuit had low overhangs, and he couldn't send the robot through the cave circuit to get within range of the other robot. And that meant he had to get rid of the drone. So he had to launch the drone, and you couldn't just launch the drone anywhere. And that's why he had to come back. You'll see it again. If you noticed in the previous video, it came back to a larger room and then had to launch the drone. So this is that happening. So this is launching the drone, because at that time, the drone wasn't going to be useful. So it was less than 10 minutes on the clock. And the whole point was get rid of the drone, send the robot in to get the data. So that's what's happening here. And then in the next video, you'll see that last remaining UGV, Bear,
drain passageways
making
and
a
those
beeline
rails
down
as
the
CSIRO
cave
Data61
circuit
pops back up
with
on
less,
up. Just
with
5 minutes
5 minutes,
left.
20 seconds on the
27 total
clock
attempts, a score
to
of
get within
21
range.
points.
And our
And
score
that
is 21
was
points
Bear
at that
without
time.
the drone. So to be able to get it back through those caverns, that was what Brendan
You'll
was
see a
thinking about.
communication
How can I
node being
cleanly get
launched.
this
You
vehicle
see
back
a
in a way?
thing falling
and
off the robot.
losing
So
the
that's
drone,
actually a
that's what it is.
communication node.
So they lost the drone and they continue on their path. How far they can get, that's the real question, as another piece kind of falls off that system.
Yeah, these are really tight passageways, and that
Oh,
system.
by the way, I didn't
it's
explain what
just
those attempts
very
mean. So you
difficult to
can't
get
just
something that
spam
wide
the DARPA
through,
scoring server with
um,
guesses.
But they
So
tried very hard on that.
you only get
All
45
right, who do we have
attempts.
next? Here's a look at the
And
drain passageways and the
so now this is another view of what happens. So this is a sped up view of the communication connectivity. So this would answer some of your questions. So if the link is green, that means it's good. If it's tending towards red, if it's even orange, that means you hardly get any data back. So that's the signal strength. And you'll see the different parts of the map coming up. And now this is not the operator's view, because the operators didn't get this view. This is a replay of all our data. So at this point, Bingo is way beyond communication range, happily exploring before it fell. And then you'll see Rat getting disabled in a bit in the middle part of the course. And the top one, that's Bluey. Blue is on a railway platform, subway platform, going up and down stairs all by itself, autonomously beyond comms range. And that's when Bluey connects to Bingo, gets all the data. And now Bluey is beyond comms range. So it's not connected back to the base station. Now it's trying to come back. And that's where it falls as well. And now there's only one moving robot, as you can see. And that's our only hope to get the remaining data. And you'll see it going into that particular room over there, not a room, like another cavern, to launch the drone. And the little cyan squares that you see, those are communication nodes that are dropped along the way. You'll see connectivity from those as well. So that's part of the mesh network as well. And finally, it comes within communication range to Bluey with less than 3 minutes to spare. And that's how we got all our data back. And that's how we scored the 23rd point. And so what's so special about 23 points? I'll tell you a little bit later. And this is yet another view of the last minute of the challenge. So this is what happens at the base station.
This is from CSIRO Data61.
So you'll see the clock, you'll see the score.
Oh, and look, they're trying to throw out some of those attempts late into this run, very late. There's another attempt. You might as well just kind of throw some out there, see if you can get a couple extra points up on the board.
From my PhD students
They're
from
searching their
UQ.
maps.
So on at the base station,
Looking at the
that's
different
Brendan.
pictures,
Brendan
seeing if
Tibb,
there's
he's a
anything that's
QB
good.
PhD student.
You know, it's better
So
to not leave
he's
anything on
in
the
front of
table
the
at the very,
computer.
very
So he's
end. Those
looking at
attempts
all the
aren't gonna
data
buy
coming
you
through,
anything if you
trying
don't
to
use
score
them.
those
So
points,
And
reviewing
that's
all the
what
data
happened with
that's coming
Explorer.
through.
Explorer had data
So
that
yeah,
came
that's
in,
the
but
23rd
came in
point that we scored
after
with about 24
3 zeros
seconds
up
on the
the
clock.
screen.
well, and that's a co-star did that same thing.
Right.
Absolutely. And you even just saw another point actually head up on the board just with a few
As I
seconds
mentioned,
left for
the
CSIRO.
teams were sequestered. So these guys didn't know what the other team scores were, but we knew because we were connected from Brisbane. So we knew 23 was the highest score at that time. So the team Cerberus, the team from Oxford, ETH Zurich, University of Nevada, Reno, rest of the world, Norwegian University of Science and Technology. So that was the team. So it was a consortium and they had scored 23 points. And they were waiting for us, our team, to come out. And when the team finally came out, they said, oh, we'll only scored 23 points. And they didn't realize that they've tied with the top score. So that was pretty exciting for us. And that's when the DARPA tiebreaker rules were invoked. And what that meant was whoever scored the last point the earliest wins. So essentially, they see how quickly you scored the 23 points. And we didn't know because the Cerberus team came and said, oh, we had roughly, like we scored the last point in the last minute. We said we scored the last point in the last minute as well, but we didn't know when exactly. So we had to wait for 24 hours. We had to wait for a day until the DARPA award ceremony to find out what actually had happened. So
This is from CSIRO Data61.
unfortunately, we came second because we were 46 seconds slower than the other team. So that's the final leaderboard. So we tied for the top score, but it is essentially a photo finish in a marathon. Like if you consider a 1 hour run, 46 seconds, that's a pretty close finish. But overall, we were pretty happy with what we did, given the journey that we came through over the last 3 years, the amount of cool technology that we developed, and the very fact that we were willing to ship our robots halfway across the world and get a team that were not used to operating the robots to operate the robots. That in itself is a testament to the maturity and the level of how should I put it? Yeah, the level of maturity of the technology, really. Because as you can imagine from what you saw, for this to work, so many things, so many subsystems have to work together. Like the hardware has to work, the software has to work, the communication system has to work, your mapping system has to work, your localization system has to work, your object detection system has to work. So everything has to work together. And this was a perfect example of all of those things coming together and working really well. And yep, so we won $1 million. So the first place was $2 million, but we still won $1 million. It was a really cool outcome. It was really exciting. And for us, it wasn't a win for our team. It was not even a win for CSIRO. It was a win for Australia because we really got to kind of showcase Australian technology and compete against the best in the world. So for those who are not familiar with the names, so first place, Cerberus, that's the consortium from Oxford, ETH, so on and so forth. So that's us. Second place, Marble is the team from University of Colorado Boulder and University of Colorado Denver. And Explorer is Carnegie Mellon University. And CoStar is NASA JPL. And CTU, that's Czech Technical University from Czechoslovakia, Coordinate Robotics, and Robotica, again, another team from the Czech Republic. So it was a pretty cool outcome to be able to beat some heavyweights in the domain. And this is a really cool and clean looking SLAM map that we got. And there's some special significance to this as well. So and the different colors are the different robots that collected this information, and this was a cool outcome as well because this was a true example of distributed mapping where the agents actually did their job without all going to the same location or anything like that. The really cool thing is DARPA, while it was not a scoring criteria, they also compared the mapping performance of each of the teams against the ground truth, the surveyed ground truth of the environment. So green means good, orange means bad. So as you can see, we are the only team that got all green. So according to DARPA's own performance metric, we got 0% deviation from the surveyed ground truth with a 91% course coverage. And even the winning team didn't get anywhere close to that. So even the winning team had a nominal deviation of about 15% from the ground truth. And not only that, what that led to was we also won another award for the single most accurate artifact report. So they considered who had the least error for the reported artifacts. So we detected that drill with 4.8 centimeter error. Just to put things in context, we would have still scored this point if that error was 5 meters. So we were 2 orders of magnitude better than the required accuracy for scoring that point.
Question on that. How big is the course in total from end to end?
Fletcher. Yeah, hang on, let's see. So each of those squares are 10 meter by 10 meter. So let's see. So what's that? 1, 2, 3, 4, 5, 6. About 180 meters.
About 200 from the...
Yeah, 200 meters by 80 meters or so. So it wasn't a very large course in those extents, but it was a very complex course inside.
This is from...
What's that? Yeah, multi-level as well, sorry. So if you see in this, like you'd see some teams actually had what seemed like an accurate map, but it's orange. That's because they were off in the Z axis. Yeah, and in terms of the performance of the robots, this is just a glimpse of what actually happened inside the robot. So each of the subsystems had different states. Finite state automata had different states. So when it's green, that means it's autonomous operation. So without any human intervention, without the operator doing anything. So we had different behaviors, different planners, different controls that switch. And then the pink ones, that's when the operator drops waypoints for navigation, and if it's red, that's teleoperation. So you'd see majority of the time, the four ground robots were in autonomous operation. The next one, it's a bit of a complex slide, so I'll try to explain what's going on. So this is Bluey, the second legged robot that was deployed into the circuit. So this is again beyond comms range, exploring autonomously. So this is detecting stairs, going upstairs by itself, and on the right hand side, what you see is all the circles. Those are the frontiers, and the yellow ones are the frontiers. So all the green lines, that's the graph. That's our topological map used for global navigation. And you'll see a global waypoint selected to go to a particular frontier. And as you can see, there's a sharp drop off there. So this is on a subway platform. And you'll soon see it decides to go down the stairs autonomously as well. So this is all beyond comms range operation. And just to let you know, like the Boston Dynamics robot, that when you get it's a fairly capable robot, but it's not an autonomous robot. It's good for remote controlled operation. So what you see on top here is everything that we've done and we've put on the robot. So even the stair mode, the robot does not automatically detect stairs and go down. And the recommended way is to go downstairs backwards. So in this case, the robot will detect the slope, detect the stairs, turn itself around, decide to go backwards. All of that is done autonomously. Question?
So how heavy is the brain that Spot carries?
The payload?
Yeah, how heavy is the brain? Not the sensors, just the brain.
Have you weighed it? Yeah. This is not something that was done real time, but just to show you. So we can colorize the LiDAR point cloud using the camera information. And this is a colorized point cloud fly through of the DARPA course. And we are lucky to have one of the authors of this system, Mark Cox, who's sitting down there in the front, who developed this colorization system for point clouds. So this is different to photogrammetry. So this is not photogrammetry. So this is a LiDAR point cloud that had been colorized point by point using the camera information. Question?
Is that is this a live recreation that you were seeing remotely, or is this just for showing other people about your project?
So this is actually post-processed. We were working on trying to do it real time, but then we ran out of time. So we didn't have it implemented for the final competition. So this is a post-processed output. All right, so a little bit more about the technology. So hopefully this will answer one of the earlier questions that you had. So one of our competitive advantages was this concept of homogeneous sensing on heterogeneous platforms. So what that meant was, so over the 3 years, we had many different platforms. Some of them we built ourselves. So this hexapod robot was designed and built by CSIRO. So was the tracked robot that you see top right. We bought a number of platforms off the shelf from local companies, from overseas companies, even the quadrupeds. We bought one from a company called Ghost Robotics, and then we swapped it over to the Boston Dynamics robot. And then we had a smaller track robot, larger track robot, but the common denominator, you'll see that you have the same CAD pack or the same sensing payload on each of the robots. So what that is, it's a spinning velodyne LiDAR. And then we have a Jetson's AVA AGX compute platform inside, and got 4 cameras around it. And that's what runs our SLAM solution called Wildcat. So that's CSIRO developed simultaneous localization and mapping technology. And all the platforms run Wildcat SLAM. And the drones, the Emerson drones, have a slightly different form factor. They have a hover map unit, which is a commercial product that they sell. And as I mentioned, Emerson spun out from our lab, and they also run exactly the same Wildcat SLAM. They license that SLAM from our lab. So overall, our full fleet has exactly the same SLAM algorithm running, which makes it a lot easier because we do multi-agent SLAM. And then on each of the robots, we have another compute payload. So in this case, we call it the barn, the black box that's behind the spinning LiDAR. That's what has the autonomy computer. So it has the local navigation and global navigation, obstacle avoidance, and all of that happens in that computer. But we had the same setup on all the robots. And that made our life so much easier to be able to easily integrate different platforms into our fleet. That allowed the robots to talk to each other quite seamlessly. And going back to your question earlier, we had to have a drone that was capable of carrying our SLAM payload. And that kind of determined the size. Yeah, so that's why a smaller drone wouldn't have worked, because it had to be a drone that could carry a LiDAR SLAM payload. Yeah. interoperability. That's the keyword. And the next slide gives a timeline of how things evolved over time. So as I mentioned, our first circuit event was in August 2019. So before that, there was an integration exercise in Denver, Colorado, where we got to take our robots to the US to test it out in a tunnel environment. So we had a different fleet back then. Our sensor form factors were a little bit different. Over time, we learned lessons, we evolved our solution. So when we went to the tunnel circuit, for example, in August 2019, we had way too many platforms. So we had a quadruped, a hexapod, 2 types of track robots. And then we realized that was a little bit too diverse. And then February 2020 for the urban circuit, we didn't take any legged robots. We just had track robots and the drones. And then when we had the cave circuit, that's when we were slowly converging to a good solution where we knew it was just the right number of agents with the right capability. And towards the end, the finals, we had this particular configuration. We also developed a track robot, the DTR or the dynamic track robot. In the end, we didn't deploy it in the finals because the plan was we would have taken it if our team from our lab traveled, but since we didn't travel, we didn't include that platform in the fleet. Oh, yes.
When you're evolving with the prototype, do you have to have the right to repair or to modify the Boston Dynamics, for instance, to add it all the other radars and whatever you have to add?
Yeah, good question. So, something that we learned over the past few years is there's no such thing as a perfect robot that you can buy off the shelf. So every single time we bought a robot, we had to do some level of modification to integrate our systems. So I think out of the different platforms, the Boston Dynamics platform probably was the easiest to integrate. So what we do is we connect to the API provided by the robot to send velocity commands to send information about where it needs to go. So the navigation is done by our system, but then we send navigation commands down to the robot, and then the low-level footstep planning and all of that is handled by the Boston Dynamics system. Now, we did something extra though. As you can imagine, when the LiDAR is spinning like that, it has some occlusion, so it doesn't see right next to the robot, so it doesn't see underneath the robot. And that prevents us from doing path planning that's really near, very close to the robot. And what we did was the robot itself has integrated sensors. So it has 5 time of flight sensors around it. So we managed to pipe that information into our pipeline and use that information fused with our mapping to seamlessly be able to plan from near to far with that robot. So I don't know whether I properly answered your question in terms of the expertise. So we do need to maintain a fleet like that. We do need electrical engineers, we need mechanical engineers, we need software engineers to do all of that. But the level of complexity in doing that for different robots was a bit different. So for example, the track robot, the one that we bought from the Brisbane-based company, we had to essentially pull out all its innards and replace what was inside. So we changed I think we changed the gearboxes, motors, the batteries, and the low-level controller inside the robot. So what remains is essentially the chassis and the tracks from, well, to be fair, it was a very challenging environment. Those are very, very robust and hardy robots. And yeah, so that kind of shows the communication node as well. So I think that I've got a video that shows what it looks like when the communication node is deployed. There's a delay and then it opens up the ground plane and the antennas come up, which is pretty cool. Arguably, maybe. So that's another slide showing the various different things that you have on the robot. So you have the Wi-Fi detectors, gas sensors for carbon dioxide detection, node launchers, comms hardware, drone launchers, the LiDAR payload, and you'll see how things are common between the different agents. And this video will show you a communication node being launched. It's not very glamorous when it falls out of the robot, but if you wait for long enough, you'll see what happens. So that's the cool bit. It self-writes, opens up the ground plane, and the antennas pop up. And you would have seen the drone being launched as well. I'll play it again. Hopefully. So all of that communication node hardware and everything was designed and built in our lab in Pullenvale. And we were able to do all of this cool stuff because of the testing facilities that we have at our lab in Pullenvale. So you'll see some of the very rigorous testing that we do to get the robots go through narrow gaps. That's what you see on the left-hand side. So that's fully autonomous. That's not somebody using a joystick to make it go through a narrow gap. So those who are familiar with doing these sort of things with robots, you'll know that sending robots through narrow gaps is not a trivial task at all. And we managed to do that. And we built all of this custom infrastructure in our lab. So we built 300 meters of shade cloth tunnel to be able to test these robots, and build those custom platforms, stairs and ramps and everything to rigorously test all of this. We were doing rigorous integration testing every Friday, every week for 3 years. And this is to show how the testing has relevance to what actually happened in the real competition. So top footage is from the actual competition, bottom footage is testing in our lab. So you'll see the stair climbing, going up, going downstairs, how that became relevant in the actual challenge. And we are not always very gentle with our robots as well.
Sorry, just a quick question. With the Boston Dynamics, was it already programmed for the higher center of gravity, or did you have to do some learning for it to be able to take us, the higher payload, the 4 and 3 kilos higher up? Was it part of it already? I know the Mule or whatever, the bigger version of that is geared to take stuff, but these ones, did you have to do any adjustments?
It has a maximum payload, but what you have to do is when you put a custom payload on top of it, it has a calibration mechanism. So you have to let it know what the payload is and where the center of mass is of the new payload, and it takes that into account for its controller. So if I play this, you'll see some footage from the real competition on the top, and then some rigorous testing that we did back home. So as I mentioned earlier, we are not gentle with our robots when it comes to testing. So we test them very rigorously. And as you can imagine, that's a really tough challenge for a robot, but that's how we test our robots. And on the top, I don't know whether you noticed, this is going through a puddle of water. That's the actual challenge.
Question.
Yes.
You spend a lot of time with these robots. Do you become more attached to them doing all these things? Or as you see them fail and you program them, do you become less attached?
It's probably a question for Fletcher, who spends more time with these robots. Yeah, we are tough taskmasters for robots, I suppose. So yeah, I think overall, I think it was a fantastic outcome. You see some more cool footage of the communication nodes doing its conga line. So we got this opportunity to really showcase Australian technology on a global stage and shine a spotlight on that. So which was a great outcome. And at the same time, we've developed and matured technology through this competition, and we've commercialized them. One example is the Wildcat SLAM technology that is already commercially available through companies like Emerson. If you buy one of their hovermap drones, hovermap payloads, you get our SLAM. And we recently also commercialized it through the cat pack that you saw. You can actually buy that from a company called Automap, again, a Brisbane-based company. And we are currently working on commercializing our navigation stack as well. So currently, we are focusing on how we can translate the technology that we developed throughout this challenge and get it into the hands of the Australian industry who actually need this technology to solve their problems. So yeah, I think that's about all I have. Happy to answer any more questions.
Awesome. I think just given where we are time-wise, I think what we might do, and especially because the microphone and speakers are pretty rubbish tonight, what we might do is we'll pause here. Anyone who wants to take off can, and maybe what we do is we come forward and do it without the microphones. I think that'd be a bit better. So we'll pause for a second. I just want to say thank you now to Navinda, Mark and Lachlan, all the team from CSIRO. An amazing result, 3 years of heaps of work, no doubt. Looking forward to hopefully seeing Spot run around a little bit more tonight. If anyone has questions, feel free to ask. To everyone else who wants to go, thanks for coming. We'll see you next year.